All right, let's talk about cubic functions. This is one more type of function, and we don't really use it in modeling at the beginning of Algebra 2 very much because it comes up in more complicated situations, which we'll talk about in a second. But it is a type of function we should recognize. The parent function is f of x equals x cubed. And the general equation is y equals anything times x cubed plus anything times x squared plus anything times x. Oops, this should be a b cx plus d. Basically, the idea is it can have a whole bunch of different things. So like an example would be y equals 5x cubed minus x squared plus 3. Notice here c is 0. There's no x term. And in the parent function, b, c, and d are all 0. There's just an x cubed, no x squareds. One thing to note about this is a lot of people think of x squared as being a quadratic, but if there's an x cubed, the cubed wins out and it makes it a cubic. So let's look at how this function works. And remember that cubed means x times x times x. It means times itself 3 times. So when x equals 0, that means 0 times 0 times 0, which is 0. Go ahead and fill out these on your own. See if you can feel good about this. 1 times 1 times 1 is 1. 2 times 2 times 2, 2 times 2 is 4, times 2 is 8. 3 times 3 times 3 is 27. And if we graph these, it starts looking like another function we should already know, where it's bending upwards, it's concave up. This looks a lot like a parabola. It's a little bit steeper. It grows a little bit faster than a parabola. But let's look at the other side. What do we get when we do -1 times -1 times -1? Well, a negative times a negative is a positive, and a positive times a negative is a negative, and so we get -1. What about f of -2 and f of -3? Well, -2 times -2 is 4, times another -2 is -8. -3 times -3 times -3. -3 times -3 is +9. +9 times -3 is -27. And so unlike a quadratic, which bounces back up because a negative times a negative is a positive, for a cubic function, we actually end up with a very different looking graph. And the key feature here is right here there's called an inflection point, and all cubic functions will have an inflection point. And what an inflection point is it's a place where it changes from concave down, in this case, or it could be concave up in a different case, to concave up. So you'll notice that this graph is like, it's bending down for the first part. It looks, if I were to zoom in, it actually looks more like this. So it's bending down for that first part, and at the inflection point, it stops bending down and starts bending up. So at this place, it changes concavity, it changes how it's bending. The domain for all cubic functions will be all real numbers, and the range will be all real numbers. And there are other ways to write that I hope you feel comfortable with. Just real quick, there are other cubic, this is the graph of the parent function. Other cubic graphs that have that one inflection point might look a little bit like this. They look a little crazier. And you'll notice it still has an inflection point right here. It was bending down, and after the inflection point, the function starts bending up. And so cubic functions end up having this inflection point. Let me briefly tell you what we use cubic, where cubic functions come up in. They come up in volume a lot. So anytime we're dealing with volumes, you'll end up with a cubic function, volume of a cube, which is where the name cubic comes from, volume of a rectangular prism or a cone, or the volume of a sphere. All of them involve cubic functions. And also rockets. So like rocket science, they accelerate upwards, and they actually go faster and faster because as they burn off fuel, that's what makes it a cubic situation, because they're also losing weight at the same time. So these are some situations we deal with cubics in, and there are others, but that's it for cubic functions for now in the year. That's kind of all you have to know is how to be able to recognize them. One more thing I want to show you in the table is the way to recognize a cubic table is that unlike a linear equation, which has a constant rate of change, unlike a quadratic function, so notice a linear function has constant difference. This has constant second difference. You might be able to predict, but maybe not. A cubic function is going to have a constant third difference. And this pattern actually continues when you have like an x to the fourth that has a constant fourth difference. Let's look. Going from negative 27 to negative 8, we have to add 19. Going from negative 8 to negative 1, we have to add 7. Going from negative 1 to 0, we have to add 1. Going from 0 to 1, we add 1. Going from 1 to 8, we add 7. And going from 8 to 27, we add 19. Now, this is not a constant difference, but let's look at the difference of the difference. Going from 19 to 17, we go down by 12. Going from 7 to 1, we go down by 6. Going from 1 to 1, we go nowhere. We add 0. Going from 1 to 7, we add 6. Going from 7 to 19, we add 12. And this is still not a constant second difference. But if we look at the difference of the difference, this is the third difference. We add 6 going from negative 12 to negative 6. We add 6 going from negative 6 to 0. We add 6 going from 0 to 6. And we add 6 going from 6 to 12. And we will notice this is the third difference. So the third difference is constant. And that's how it will always be for cubics. So if you suspect a table might be cubic, you just check the first difference. If it's constant, it's linear. If it's not, you can check the second difference. If it's constant, it's quadratic. If it's not, you can check the third difference. If it's constant, it's cubic. So that's it on cubic functions for this part of the year. We should be able to tell the graph by their inflection point, the table by their constant third difference, and we should be able to tell the equation because it'll have an x cubed somewhere in it. Although sometimes this shows up funnily like y equals x minus 4 cubed. This is still a cubic function because the x is being cubed. All right, guys, that is it for this.